At this point, we're going to very briefly talk about turbines, impulse and reaction turbines. Now, the basic equations for turbines are very similar to pumps, but we have to remember the sign convention on work and torque. Head loss and pressure change are negative across the turbine. Now, in order to characterize a turbine, to measure how it behaves, we use what's called a dynamometer. That measures the turbine output power, the speed, and the torque. We use a tachometer to measure the speed, basically the revolutions per minute, and we use what's called a torque arm to measure the torque developed by the turbine. And then power can be calculated as the speed times the torque. Like pumps, we can use the Euler-Turbo-Machine equation to analyze ideal systems, and like pumps, we generally rely on empirical measurements to fully characterize turbines because of the difficulties modeling things like boundary layer separation and friction losses. Now, impulse turbines are used for high head, low flow situations. Something like a Pelton wheel, where a water jet strikes a series of buckets, and the momentum of the water forces the buckets around the turbine. These are operated at constant speed, and then the power they produce is adjusted by changing the jet area. You can see on the picture here, there's a hand wheel which moves this sphere, and at the end of the sphere is a variable area plug that changes the flow area of the water through the nozzle. When we're analyzing these types of hydraulic turbines, we have a few parameters we need to define. The first is the gross head. The gross head is the difference in height between the reservoir and the exit, and it basically measures the head of the reservoir of the fluid. The net head is the head at the entrance to the nozzle. So basically there's some friction loss that's accounted for when you calculate the net head. The peak efficiency of these types of systems and the peak power occur at the same conditions. At low heads, reaction turbines provide better performance. This is basically the opposite of a centrifugal pump. They tend to be high flow and, again, low head. They are always full of fluid, and there are two major types. The first is the Francis turbine, and the second is called the Kaplan turbine, also called an axial flow turbine. Each is best for slightly different operating conditions. The axial flow turbines tend to be better at higher specific speeds, and the Francis turbines tend to be better at moderate specific speeds. What's really useful about these types of reaction turbines is that you can add a draft tube to the exit. It's basically a diffuser that expands as you move away from the turbine. And so what this does is you have a higher flow speed at the exit to the turbine than at the exit to the draft tube. And going all the way back to Bernoulli's equation, a higher flow speed means a lower pressure. So if the exit of the draft tube is at atmospheric pressure, that means the exit of the turbine can actually be at lower than atmospheric pressure, and that can help improve the power output from these types of turbines. So in this case, the net head is actually the difference between the turbine entrance and the draft tube exit. So we have that new definition for net head. Now, the power produced by these types of turbines is not free. The operating costs are low, but you need to provide a water source. And that usually means that you have to build a dam or have some other type of reservoir. So capital costs are high, and they have to be evaluated for environmental damage. Steam and gas turbines are governed by essentially the same scaling relationships as compressors. In fact, many of the governing equations are the same. It's actually a type of axial flow turbine with compressible flow. Now, these types of devices don't have performance that's a strong function of the speed. If you look at the corrected mass flow rate and the specific speed and so on, the performance of these turbines is not a strong function of the specific speed. They do have a very well-defined choking limit, where as the pressure ratio increases, you cannot continue to increase the mass flow rate. So you can definitely see the maximum mass flow rate that you can produce through one of these systems.